Our next keynote speaker is Professor Subbarao Kambampati. Professor Subbarao Kambampati is a professor of computer science at Arizona State University and one of the world's leading researchers in automated planning, model-based reasoning, and human-aware AI. He has served the AI community in numerous leadership roles, most notably as the president of AAAI from 2016 to 2018. He is an AAAI fellow and a AAAS fellow and has received multiple awards for both research excellence and mentoring. Beyond his technical contributions, Professor Kambampati is widely recognized for his thought leadership on the capabilities and limitations of modern AI, offering nuanced perspectives on LLMs, data-driven AI, and the future of human-centric autonomy. We are delighted to have him with us today. Without further ado, please join me in welcoming Professor Kambampati for the next keynote titled, Do Thinking Traces of Reasoning Models Really Offer an Interpretable Window into Their Thinking? Thank you.
Thank you. Thank you, folks, for the invitation as well as for attending. So I'm going to talk to you.
No, just go in here.
What?
You're fine there.
Okay. So I'm going to talk to you about basically the thinking traces, which all of you know. These are the intermediate tokens that the LLMs reasoning models generate. And I want to tell you about a bunch of tests that we have done about their semantics as well as their connection to complexity of the problem, etc. Just to get all of us into the same perspective. So obviously we know that there were standard LLMs, which were just basically pre-trained on the quote-unquote declarative data that we put up onto the web. And then the reasoning models, which are basically standard LLMs, which kind of can be seen as essentially also trying to kind of benefit from the procedural knowledge that we have, for example, in terms of verifiers. These are standard LLMs with the test time scaling and post-training to kind of improve their performance on some of these tasks for which they are verifiers, the reasoning tasks and so on. And then so for the test time scaling, there are a bunch of ideas which are basically at the time of inference, the LLM takes more time trying to check the verify using whether the solution is correct, or probably generate a lot of traces and see if some of them, the majority has some property, etc. So basically spend more time during the online user-facing time, and that actually especially if you use LLMs as generators, and then you actually have a verifier in the loop, what we call LLM modulo, that gives guarantees modulo the verifier's properties. That much is well known. The interesting thing, of course, is spending time at the online user-facing time is very costly, and people don't want to wait at all. And so one thing that you can do is basically try to do some of the stuff in the online in the offline or the training phase. So as Marvin Minsky actually said, the intelligence is integrating test part of generate test into the generate part. And you can actually think of post-training really as doing that. All they basically do is they take they kind of generate synthetic problems. They try to solve them by trial and error during the training. And then they use the verifier signal to actually generate basically correct traces, and then you can either fine-tune them either as SFT or RL. And in fact, we'll see that what is being called RL in DeepSeek R1 is really SFT. It turns out because of the way it actually splits the reward basically into all the tokens. We'll get to that in a minute. So there's the post-training approaches. This stuff I assume you all know. You're all very smart people. You are in NeurIPS. In general, I tend to think of what's happening in the post-training essentially as you have the verifier signal. Basically, this is a procedural verifiers, algorithmic verifiers that we have, and that the signal is being slowly, ever so slowly compiled into the generator using these post-training approaches. And so, in fact, part of the thing is we would like for them to have learned the algorithm, but that's not what is actually likely happening. They're trying to fit themselves to longer and longer traces of the unfolding of the algorithm, and that sort of explains what's actually going on in terms of their performance. We'll get to that in a minute later too. So that's the thing to have. So that gets us to the main point of my talk, which is there are some questions that I'd like to kind of for us to ask, because these are taken for granted. If you're walking around in the NeurIPS poster sessions, these are all taken for granted, and I'm going to question them. What's the role of intermediate tokens in large reasoning models? In particular, are they really supposed to help the end users understand what the LLM is thinking? Are the interpretable intermediate tokens actually better at all for performance? And then finally, is the length of intermediate tokens a reliable indicator of the difficulty of the reasoning problem? If you put out more reasoning tokens, let's say during inference, does that mean the problem is harder? And similarly, how do you answer all of these when you throw in this post-training RL stuff? In particular, how reliable all the claims around RL formulation in terms of learning to reason, and also thinking of intermediate tokens as measures of reasoning effort. So it turns out that one of the nice things about this talk is even if it flies by too fast, there's a whole bunch of posters about each part of this talk that are being presented here, right here in the workshops by my students. And any advisor ultimately is a Vincent adult man, basically with their, kind of trying to misrepresent their students' work. And so that's basically what I'm doing right now. Let's get to the intermediate token semantics. The first is, I want to first differentiate two notions of intermediate token interpretability. One is trying to understand what exactly are LLMs and LRMs doing by outputting intermediate tokens. How are they actually improving performance? This much we know. With the traces being thrown in during the training as well as being output during the inference, the accuracy is improving. There's no question. The real question is whether those intermediate tokens, they obviously help LLMs. Do they also help humans? Do they also help actually end users in terms of having some sort of semantics? So the mechanistic interpretability part tries to see why are they helping the LLMs. I'm fine with that. The second question is, how are the intermediate tokens actually helping end users interpret the quote-unquote inner thinking process of LLMs? This stuff, there's a whole bunch of anthropomorphization on this. There's the aha movements, there's the thoughts. Of course, we go out of our way to call these things thoughts and then say, I must be thinking, because we said it's thoughts. Reasoning behaviors, the models are thinking through the problem, they're backtracking, they're self-verifying. And the problem, of course, is when you are training the models with traces that seem to say things like I'm backtracking, etc., they're going to definitely imitate the style. Imagine I'm talking to you on the phone and you're asking me to do, I would like to do the following thing. I want to improve my weight, so I want to have like a physical fitness thing, except on the phone. And the guy is on the phone and they say, Rav, are you crunching? Yeah, I am crunching. The question is, am I actually doing it is the real question, right? So anthropomorphization obviously I'm doing this, I guess that's why I'm like this. But anthropomorphization of intermediate tokens is very much there. So the question is, are they really generating some sort of representation of what they are currently, what actually they're doing, saying versus doing. So there's an expectation that the intermediate tokens output LLMs are like actual reasoning traces about the LLMs, but there is little reason to believe that. But the problem, of course, is it's hard to verify one way or other for frontier models. For example, take DeepSeek R1. By the way, remember that we are in this crazy world where instead of trying to learn the secrets of the nature, we are trying to learn the secrets of OpenAI and Gemini and various other guys who know what they're doing, but we have no idea what they're doing. Thankfully, DeepSeek R1 people at least wrote a paper. I'm extremely happy that they wrote a paper about what they're doing. So science is about falsifiability. So because they wrote the paper, I can question exactly what's going on in their work. It's not any insult to them. The fact that I can't do it for Google and OpenAI is a shame on them, not as far as science is concerned. So R1, basically, we give a small block sort problem, and then it basically outputs this kind of intermediate tokens. So I can just say, wow, it looks like English. So basically it says my goal is to achieve object C, K, object A, blah, blah, blah. Looks like this. What do you mean, Rav? This doesn't have any meaning. Of course, it seems to have meaning. First of all, this is the first page of this very small 3-block problem, okay? Second page, third page, fourth page, fifth page, 5 pages of mumblings. You would die trying to make sense of them. This is just mind-numbingly, bland English. It all looks locally like it's saying something, but can you actually read this whole thing and say, is this the reason whether the solution became correct? it's impossible to do so. So what happens then is this is like the Rorschach test. You see the ink blot test and say, wow, that it said I'm backtracking, so it must be really backtracking. And Ralph said he's crunching, so he must be crunching. That is not the way you should be checking, right? So what we do, so in fact, I called these sorts of LLM, this sort of anthropomorphization, sort of LLMs, LRMs should be called LMMs, large mumbling models. And the mumbles may or may not have accuracy. We do know that the solution accuracy improves, but it doesn't necessarily mean that their mumbles have any semantics. So by the way, I actually happen to be one of the reviewers for the Nature paper. Nature actually makes it open as to who reviewed the paper for R1, and I tried to push them back on the anthropomorphization. And in fact, they did to some extent. But I'm going to then specifically to look at this issue of how do I evaluate whether or not intermediate tokens have traces have semantics. You need to do more focused study. And this is the first paper that we're going to look at, which is this beyond semantics that's being presented in the workshops here. So what we wound up doing there is we took a star search to kind of solve a bunch of maze problems. And the A-star search, if those of you remember A-star search, it does open closed list manipulations. And so basically does, I'm going to put this node on the open list, I'm going to take it out, put it on the closed list, all this stuff is the trace. And one of the nice things about that trace is A-star actually can reinterpret the trace. If I give it a trace, it can actually simulate it to see if it reaches the goal or not. So we generate a whole bunch of synthetic problems and then let A-star search solve these kinds of mazes and let A-star search solve these problems and then essentially train an empty transformer with the problems, the traces, and the correct solution that the A-star search has provided. And of course, for the control study, we also train them with just the problem and the solution. And not surprisingly, problem and the solution version doesn't do as well as problem and the traces and the final solution. Looks good, right? Up until then. And also we do this very carefully in terms of looking at different kinds of distributions of generating mazes so that you can also talk about whether this is out of distribution versus in distribution, etc. There's a bunch of different ways of generating mazes and we do all that stuff. Okay, so one of the advantages of doing this is now after having trained the transformer model, you can essentially let it solve a problem at the inference time. And unlike people who say, since the solution is correct and it also seems to be mumbling, the mumblings must be correct too, we can actually take the mumbles and then simulate them. Right? And so there's a trace validity, there's a solution accuracy. And we can actually compare trace validity and the solution accuracy. And so what we find is, first of all, even in the smaller cases, trace validity is not 100% correlated with solution accuracy. And as the problem length increases, as you can see in the second table, as the problem length increases, the last line of the second table is saying that when 16.2% of the plans are actually accurate, only 50% of those plans have an actually valid traces. The rest of them, basically, if you try to do those traces, they won't produce the plan that the system said it produced. So this is basically Rav saying, I'm crunching without actually crunching, okay? Now, once you hear this, you realize, does the correctness of the trace, if in fact, when it's only mumbling in the final stages, does the correctness of the traces during the training matter? Did I have to really make sure that A-star search correctly solved the problem and showed the correct trace to the thing? So what did we do? We actually considered the following modification, where you take problem 1's trace and swap it with the problem 2's trace, problem 3's trace with the problem 4's trace. So everybody has wrong intermediate traces, but the correct solution for that problem. And then we retrain the transformer with this highly corrupted, basically swapped data. Now, what would you think? Obviously, if correctness matters, it should probably die. Unfortunately, it doesn't die. What's worse, it does better than a transformer that is trained on fully correct traces. This is crazy, right? That basically means that the correctness of the trace doesn't seem to matter. Okay, so what else did we do? We actually did one extra experiment where we started with 100% correct traces and 25% noise, that's 0% noise, that means 100% correct traces, no swap traces. 25% of the problems have swap traces, 50% have swap traces, 75 and 100% swap traces. So we now trained all these transformers separately. And for each of these transformers, we again checked whether during the inference time, how is the accuracy and validity going to be affected. It shouldn't be surprising that the trace validity will fall down because basically, it's sort of being trained on things that are not correct to begin with, so it actually trace validity does fall down. What's mind-boggling to some extent is the the solution accuracy has a U curve. It's actually high, falls down in the middle, goes back high. What that seems to suggest is it's not the correctness that matters, it needs a sort of a consistent scaffolding with respect to which it can train itself, overfeed itself to the solution accuracy signal that it's getting. So that's basically what the results are here. Okay, so this is actually being presented at law and for LM workshops. You can go get a lot more information about it from the students who are presenting them. One other issue here is, does the length of the trace somehow have any connection to the problem complexity? Okay, this is another thing that people say because, like basically the longer you talk, it's like one of these weird scenarios where we are only paying for the tokens to Sam Altman. So we somehow think that's the compute thing. And so we are trying to say that that compute is connected to the computational complexity. In general, computational complexity of the problems is a terrible metaphor for understanding LLMs, which need to be understood in terms of memory of the data that's been trained on and the way the conditional distributions are being constructed. Okay, so we checked this, we took the same transformers, and we essentially take the transformer that's been trained on, let's say, a very complex normal mazes, and then ask it to solve this really silly problem, no maze mazes, which exactly has the same format, except there are no walls. So S to G, you can go directly. A star search goes directly without any problem. You give it to LLM, the transformer, it dies ignoble death. It's basically mumbles, 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 and doesn't get to the goal. What's wrong? If in fact computation complexity is what is connected to the traces, it shouldn't have happened. It turns out that it's not computational complexity. The traces really should be understood in terms of LLMs or LRMs trying to kind of think of them as the prompt augmentations that are adding to the problem such that the probability that the completion would correspond to a solution is being maximized. That's it. The rest of it, we are trying to throw in these extra things, right? So we actually check not just that silly problem, but in general, on the x-axis, the length of the trace as generated by A star search, and that's really directly connected to the hardness of the problem. And on the y-axis, the length of the trace, intermediate trace generated by the model during the runtime. And if there is any correlation, if there is a God in the world and if there is correlation, there should be some kind of a straight line, and you start seeing that basically nice scatter plots that are like all square. Okay, so everything can be connected to everything. So there really isn't any correlation between, direct correlation between the complexity of the problem and the trace that's being generated. It turns out that we have more work in the actual full paper trying to differentiate between in distribution versus out of distribution, and that's more nuanced stuff that you should read in the paper, but this is an important thing to keep in mind. Again, this was a paper that was presented yesterday in an efficient reasoning workshop, performative thinking, the brittle correlation between chain of thought length and problem complexity. And apparently I was told that some students, after hearing this whole thing, was asking my students, but you guys are contradicting everything that's going on in efficient reasoning. Well, sometimes emperors have diaphanous clothes and somebody has to point that out. Okay, so how is RL post-training going to affect all these things? Let's look at that. Now, first of all, before going into that, let's understand that RL in R1 is not really RL. If you understand RL, the whole point of RL is if you get the signal for the reward at the end, outcome reward is what R1 uses. You should let the reinforcement learning process figure out how to split that credit into the actions that led to the final solution. But that's too costly, so R1 guys basically say, well, we'll just give everybody equal weightage. If in fact you are in the winning team, all of you get a certificate. That's basically what R1 does. That's not what RL is supposed to do. And so basically reward is given for solution part, but it's distributed over the full trajectory. The same reward is given to everybody. It's like being on the winning team. You get the, I guess, a copy of the ring or something. But that's not RL. And in fact, if you think of what SFT is, and you start doing a version of SFT which uses filtering, rejection sampling, and also using the current policy to generate the next token and next trajectory, and you start from the reinforcement learning and you make these kind of crazy reward assumptions, you become essentially come to the same point. So in fact, filtered iterative supervised fine-tuning is very much similar to R1's RL with GRPO. That's just, you have to understand that. And so all these cottage industry of papers saying SFT versus RL, SFT memorizes, RL learns, etc., very questionable. RL as an idea is a great idea, but the RL that's being done by R1 that people are building on essentially is an SFT. Keep that in mind. And in fact, there is a paper on that which we presented, I'll show you in a minute, that shows also that the performance is very much similar between ISFT and RL. And secondly, one other interesting question about this mistake is that it turns out that because of the way you split the reward, the traces are incentivized in such a way that the model basically generates longer traces for the failing and shorter traces for the successful ones. And so when DeepSeek R1 said, wow, it's learning because that length of the traces is increasing, if you split it into failing and successful ones, you'll see that most of your increase in length is coming for the failing traces, not for the successful traces. I don't want to actually celebrate that kind of a thing. That seems kind of a silly thing to do. Okay, so this paper actually, RL in name only, analyzes the structural assumptions and post-training in LLMs, is being presented in law and for LLM workshops, actually, so you can go and talk to the students. Okay, now, given that we know this RL stuff, the question is, how does doing RL change any of the results I told you about there not being much of a correlation between the trace validity and solution accuracy? It turns out RL winds up increasing the solution accuracy even if in fact the traces were starting with swap traces. That means even if it's incorrect, RL improves the solution accuracy. And it's not like RL suddenly improves the semantics of the intermediate tokens. That's actually described also in the Beyond Semantics paper. One other thing that people may be confusing is RL might be improving local coherence without changing the total validity. So there's a work on actually looking at GSM-8K traces instead of these A-star style traces and checking whether what is happening with RL in terms of trace validity versus the local patterns, such as one small local pattern is doing a correct logical deduction, etc. And it turns out that's actually is what might be happening because the local coherence improves even though the global validity has no connection. Okay, this is a paper also being presented today, or actually presented yesterday, local coherence or global validity, investigating RLVR traces in math domains. Okay, then the next is this an artifact of maze problems? I already told you we use GSM-8K too, but mostly we seem to be using A-star search. Maybe it's only A-star search problem. Everybody wants to hate A-star search. Maybe it's not a problem for other things. Well, unfortunately, that's not true. We also did this work for question answer benchmarks, and there are two papers that are being presented today about that, basically showing like CoTem question answering data set. Basically, we generate both interpretable traces that can be verified and then train the model versus just let it train using R1 traces, for example, and we find very similar results that actually the correctness of the trace you are training with has nothing to do with accuracy. So the trace validity and accuracy are decorrelated. So that's a paper called Interpretable Traces and Unexpected Outcomes that's being presented in the Cognitive Interpretability workshop. And then one last question on this thing is, I think this is kind of connected to something that I think earlier on Noah was pointing out, that if in fact there's no semantics, right, you might be saying, should I train the model with optimal trace or non-optimal trace? It turns out if there's no semantics, it doesn't really matter about the optimal versus non-optimal, that stuff that you are looking into it what the model is looking is enough of a scaffold to train itself onto that scaffold and overfit. So that's what we need to understand. So with respect to that, we actually checked whether in fact interpretability of the traces, end user interpretability of the traces is at all correlated with the efficiency or the accuracy of the model using those traces. So we compared these verifiable traces that people do seem to understand using IRB generate, IRB approved human subject studies. We showed them both the verifiable traces that the model can produce and R1 style traces that we use to distill the model, and then it generates R1 style traces again. We show it to humans. Humans basically get sick and tired of R1 style traces because they're long and they're mumbling, meandering. They're much happier with these verifiable shorter traces. But unfortunately, the model's accuracy is much better with the mumbling than the interpretable one. Do you see what I'm saying? So you should actually avoid separate them. So there's a paper again in the cognitive interpretability and law workshop saying, do cognitively interpretable reasoning traces improve LLM performance? The answer is no. So as summary and a very helpful way, intermediate tokens produced by LRMs don't need or seem to have any semantics, even though they copy the style. LLMs copy every style. So why would you think they won't copy the intermediate token style? Solution accuracy can increase even when we train the model with incorrect traces. I showed you that, and that should not be surprising. And if you're not impressed by that, then you should be thinking, what am I giving this additional semantics to? What seems to matter is the consistency of the traces used in training to some extent. What helps the LLM versus what helps the end user in terms of interpretability are often at odds. That's what I was showing you in that interpretability study. That sort of connects to, should we train it with optimal traces versus mumbling traces? Actually, the model doesn't care. It can get used to, we do need to figure out what kind of scaffolding allows it to overfit itself well. That's the stuff we should be thinking about instead of counting how many times it say, I'm backtracking, I'm going to self-reflect now, etc. Those are the words it saw in the traces that were in the original pre-training data. So why won't it say that? You should be asking yourself that question. And then finally, RL doesn't seem to change much of any of this. And by RL here, I mean the DeepSeek R1's RL, which unfortunately is somewhat of a bastardized RL with essentially, it's become basically just sort of shortcuts the whole point of RL, which by just saying the outcome-based reward is equally given to all the traces. When you do that, you are essentially doing SFT. That's exactly what happens in SFT. Okay, now let me say something, question about, well, clearly it's improving accuracy, but none of the things that we thought the reason why they're improving accuracy are not working. Why is it actually improving accuracy? First of all, we'll realize that the style of intermediate tokens basically imitates the style of tokens in the training data. This is exactly what any LLMs do. Their style are vibe machines. But the semantics don't really seem to matter, as we have shown, and so why do the intermediate tokens help? One way of thinking about it is prompt augmentation. Actually, it's sort of connected to the very first thing that Noah Goodman was saying early in the morning. After that, he said stuff that I don't necessarily agree with. We can have discussions on that. But the first stuff basically that he said essentially was, it's a memory machine, and essentially what you're doing is this prompt augmentation. Basically, these intermediate tokens are prompt augmentations on top of the problem prompt, and you're trying to pick what else, what should I tell myself so that the conditional distribution will have a higher chance of corresponding to the correct solution. And this is what the learning objective should be in training the LLMs. And if you realize this, one of the advantages of this is if you know that people don't care about what I am mumbling, I can mumble in nonsensical languages. Okay, in particular in the case of LLMs, you know that LLMs, they're basically thinking in terms of points in the embedding space. Every word has a point in the embedding space. Every point doesn't have a word in the embedding space. So every other points which don't have words in the actual vocabulary, they can be thought of as superposition, using linear algebra ideas, superposition of words. So the LLM actually can tell itself mumbling stuff that since nobody is supposed to make any sense of it, it can tell itself in terms of these continuous latent space tokens. And if you've heard of things like continuous latent space tokens, such as Coconut, etc., you can make sense of what's happening there by allowing the LLM to tell itself random stuff that doesn't necessarily have to make any sense to you. It only needs to help it optimize the accuracy of the solution. And it's like sort of when you're singing in the bathroom, it doesn't really matter what kind of clothes you wear when you're practicing your singing, but when you come to the concert, you better wear good clothes and sing well, right? That sort of thing. So the intermediate tokens no longer are actually basically supposed to make sense to the end user, and keep that in mind. And so now the final question is, why am I going on and on about this? Why not let people feel happy that intermediate traces do have semantics, and maybe they are in English, and so maybe the LLMs are telling us what they're thinking. Well, the problem about anthropomorphization is they can engender false and undeserved trust in the end users. And I do not want to do that with powerful AI systems, right? And furthermore, I also told you, even from an efficiency perspective, it's an albatross on the learning if you tell them that you must only talk in coherent sentences. All of us talk to ourselves while trying to solve problems. There's an internal monologue. But if I tell people you must talk in complete Queen's English when you are talking, I'll stop talking. I'll stop doing problems. Instead, we can do any random kind of mumbling, even those that cannot even be vocalized, as long as it's sort of helping our thing. That's a bad cognitive science analogy, but it's actually computationally true with coconut-style systems, that it basically saying that these things should have semantics, but I'm not anyway going to check the semantics, which is what has been happening. He's becoming an albatross on the trading unnecessarily. So we also wrote a position paper saying stop anthropomorphizing intermediate tokens as reading and thinking traces, which essentially summarizes all this stuff. And that too is being presented in the law and cognitive workshops. You can come and yell at me more while I'm in front of them. And one final thing, because this is about algorithmic reasoning, one interesting question is, people sort of assume that you can learn algorithms from traces. It's not that easy. There are parts, even before LLMs, there's a whole area in neural networks which has been looking at, think of things like CLRS data set, where you take various, algorithms and then, convert the traces of the algorithms and then basically try to reinvent the algorithm from the traces. In fact, Kyung-Yun in his plenary basically was hoping that that might happen. But in his case, unlike in the CLRS case, he doesn't even know what the algorithm is supposed to be. But when you have the actual algorithm, you can set up very careful studies to see whether the solution accuracy is connected to trace fidelity. One other paper that we are not presenting here, but student is here, about quantifying mechanistic gaps in algorithmic reasoning, where we basically look at the specific internal activation patterns of in this particular case, it's not a transformer, it's a graph neural network, and then try to compare it with respect to what the patterns would be for the actual algorithm. And we find it's the same sort of disconnect occurs there too. Their accuracy is being improved, but it's not necessary that they're directly learning the algorithm. So in summary, again, intermediate tokens basically should be taken as something that helps LLMs, and we should celebrate that, but don't put too much semantics into it. Please stop doing computational complexity metaphors in understanding LLMs. You will really benefit from that, because essentially most of their operation should be understood in terms of essentially a memory effect of pre-training data and any prompt augmentation changing the conditional distribution. And if you start thinking about it, you would actually get better accuracy, and you would avoid doing unnecessary anthropomorphization. And obviously, I may be wrong, but we have all these papers, so you have falsifiable ability to take our papers and kill our experiments. I would be very happy to do that if you do that. And I also hope that if there are better ways in which LLMs are being trained that Gemini and OpenAI know, one of these days maybe they will actually write a paper so that we too can falsify that. That's all I have. Thank you for your attention.
Thank you so much for the excellent keynote. If you have questions, maybe we can take one question. Go ahead.
Thank you, Professor. Somdev from Intel Labs.
Can I take the second one too? Because,
okay,
yeah,
sure.
Go ahead. Yeah, go ahead.
Fascinating talk. Correlates a lot of findings that we've been doing in our lab as well.
My question is on the usefulness of the intermediate tokens. I mean, if we take the whole interpretability part of it out of it, what are your thoughts on co-optimizing the length of these tokens, which obviously has an implication on dollar cost and computational cost, and the usefulness of the final output?
So the point about the whole efficiency stuff, and there's a huge cartoon industry. I mean, I was like rolling my eyes so that they were getting into my head while walking through the poster sessions about efficiency. Basically, what they're doing is we are paying per token to Altman. We need to reduce it. And in fact, there's one idea that actually somebody was talking about, which essentially involves maybe generate many more trajectories during the training phase and then sort them in terms of length and then only take the top 15 trajectories and then retrain the model that way so that maybe it will talk less that way. First of all, you have to understand that if you sort them in terms of length, you're going to likely have more winning trajectories because of this of a signal to the RL. By doing this. And the second thing is the entire process can be understood in some sense as you're readjusting your shelf space so that you can do fewer operations in actually combining things together, as against actually changing anything about complexity. As long as you're being charged only for the tokens, I'm sure you want to reduce the number of tokens you will bring out, but then it's not coming out free. In fact, these people who do this, they do additional pre-training, additional fine-tuning. And one of the greatest scams right now that we can do is nobody cares about how much time we are spending during the training phase because Sam Altman is paying for it and Google is paying for it. And the question is whether it's actually being amortized over the queries that you're doing later on is something that we'll hopefully figure out, hopefully before any bubble sort of bursts.
Do you have a favorite approach to do that co-optimization, assuming that the cost of pre-training is a thing we are stuck with right now?
I don't have any specific favorite approach. I'm just saying that basically think of this as reorganizing the memory, and then that will give you better ideas.
Thanks.
Hi, Peter.
So you've thoroughly shown that large reasoning models are really just large mumbling models. And, mumbling is better than not mumbling. But at the end of the day, we want to have large reasoning models, damn it, right? And how do we do that?
So first of all, there are two very different points I want to make. One is the way large reasoning models work, according to me, essentially is that they are incrementally compiling incrementally compiling the signal of the verifier slowly into the generator.
Right.
Okay. That's an inefficient way. But basically just the fact that they can do, let's say, a 10-length plan doesn't necessarily mean they can do 20-length plan. You have to retrain them, bootstrapping starting from there. That's what actually happens in the DeepSeek training. This is a very inefficient way, but if you don't ever need to generate longer plans than about 100 actions, maybe this is okay, right? From a practical perspective, from a different point of view of can I learn the algorithms directly without having to overfit to the traces, that is a worthwhile thing to do, but there's actually other communities, including in neural networks, the other part of the deep learning, where they are looking at what sort of specific architectures might basically be able to capture a particular algorithm with enough training correctly. I don't have a pat answer to you right now. I do realize that they are not quote unquote learning the algorithm, but they're useful. Right? And I'm happy to use them. I have no problem in using LLMs. I just want people to not misunderstand what they're doing. Thank you.
Let's thank the speaker once again.